Dear friends, welcome to the lecture of real analysis. In this lecture, we shall study some theorems on functions. In our last lecture, we have studied the definition of function and different types of function, one function and onto function. Also, we have studied what is the inverse function. We will revise it. Inverse of a function, if f is a function from a to b and which is 1, this is necessary for existence of inverse. Then f inverse is function from b to a. Now b is the domain and a will be the codomain, such that if f of x is equal to y, then f inverse of y is equal to x. So this we have to remember, or that means f of x is equal to y implies and implied by f inverse of y is equal to x. So this is the inverse function. For example, if f is from a to b defined by f of x is equal to 2x, then this is certainly a 1 function. Then how to find its inverse function? So let suppose let y is equal to fx, and that will be equal to 2x, and from this we can find the value of x in terms of y, or therefore 2x is equal to y, and therefore x is equal to half y, or y upon 2. But what is x? X is f inverse of y, and that this is equal to f inverse of y is equal to y upon 2. Or replacing y by x, the inverse function becomes f inverse of x is equal to x by 2. And thus if fx is equal to 2x, then its inverse function is x by 2. And that means here the image is a double of the inverse image, and conversely the inverse function, the image will be half. So it is x by 2. This is easy to understand. See, if this is the function f from a to b, it maps say element 2, 3, etc. The image of 2 will be 4, 2 into 2, and image of 3 will be 2 into 3, that is 6, and the inverse image of this 4 will be 2 by this f inverse of x, or you can say y, f inverse of y is y by 2, that is 2, and similarly the inverse image of 6 will be 3. So this is the meaning of inverse function. Now we shall study some theorems on functions. The theorem 1 is, if f is a function, we will write in short as f is a function from a to b, x is subset of b, y is also subset of b, then f inverse of a union b, instead a we shall consider x, f inverse of x union y is equal to f inverse of x union f inverse of y. Or inverse, this can be written as inverse, the inverse image, f inverse of some element or set will be inverse image, the inverse image of the union of two sets. The left side is the inverse image of the union of two sets, is the union of the inverse images. See, this is we have written inverse. F inverse of x union y means inverse image of the union of two sets is equal to union of the inverse images of the sets. Now it is easy to prove the theorem. So what we shall have to prove the equality of these two sets, and when we shall say the two sets are equal, if first is subset of second and conversely the second is also subset of the first. That means a is equal to b. We say the set a is equal to b if and only if a is subset of b and b is subset of a. And again, when we say a is subset of b, that is x belongs to A implies x belongs to B. That is if and only if. IFF means if and only if. X belongs to A implies x belongs to B, and if B is a subset of A means x belongs to B implies x belongs to A. Or in other words, that is A will be equal to B if and only if x belongs to A implies and implied by x belongs to B. X belongs to A implies x belongs to B means A is subset of B, and conversely x belongs to B implies x belongs to A means B is subset of A. So we shall use this relation to prove the equality of these two sets, and for that purpose we will suppose let A be an element in the left side set. A belongs to F inverse of x union y. So this implies if A belongs to F inverse of x union y, then that will imply f of A will belong to x union y. This implies f of A belongs to union of x and y. This is by definition of the inverse. Say this f inverse is shifted on left side, it becomes f. So A is in the inverse image of x union y means f of A will be in x union y, and this is two-way implication. So this implies and implied by, again this implies and implied by f of A is in the union means f of A is in x or f of A is in y or belongs to y. F of A belongs to x or f of A belongs to y. If there is union, the logical connective is OR, that we have studied in set operations, and this implies and implied by. Double implication we are writing so that we can get the two relations in the same steps. So if f of A is in x, this will imply A belongs to f inverse of x. Again shifting this. So what we have written about if y is equal to f of x, then this implies and implied by f inverse of y is equal to x. So this must be remembered. How to interconvert the statements in terms of f and f inverse. So that we are writing if f of A belongs to x, then A belongs to f inverse x, or A belongs to f inverse of y. And again what this implies, A is in this set or A is in second set means A is in their union. So this implies and implied by A belongs to f inverse of x union f inverse of y, and thus the double implication we have started from this. A belongs to f inverse of x union y, and that implies A belongs to f inverse x union f inverse y, and that implies and implied by means two-way relations holds, and therefore the first set is equal to the second or last set. That means f inverse of x union y is equal to f inverse of x union f inverse of y. So that proves the theorem, and this shows that, or therefore we can write, therefore these are subsets of each other. Therefore the first set f inverse of x union y is subset of the last written set f inverse x union f inverse y. That is the forward implication, and converse implication gives and the second. That means if A belongs to this, that implies A belongs to the first set, means the last set written f inverse x union f inverse y is subset of f inverse of x union y. Hence these two are equal. Hence f inverse of x union y is equal to f inverse of x union f inverse of y, or that means inverse image of union of two sets is equal to union of their inverse images. So this proves the theorem. Now we shall consider the second theorem. So as if the exactly similar result holds for intersection. If f is from A to B is a function, x is subset of B, y is subset of B, then f inverse of, so this will be our second theorem. then f inverse of x intersection y is equal to f inverse of x intersection f inverse of y. And inverse, the inverse image of the, instead of union we have to write intersection. The inverse image of intersection of two sets is the intersection of the inverse images, intersection of two sets. And now this can be proved in exactly similar way. So in place of union there is intersection. See, I can change here as A belongs to f inverse of x intersection y. Then that implies and implied by f of A belongs to x intersection y. And now see, if fa belongs to x intersection y, that implies and implied by f of A belongs to x. For intersection the connective is and. It must be in both, and therefore we have to change or by and, the logical connective. If an element is in the intersection, then the element must be in both the set. It must be in x and it must be in y. And similarly, this will imply f of A belongs to x means A belongs to f inverse of x, and the connective is and. A belongs to f inverse of y. And because the connective is and, A belongs to both these sets, therefore A belongs to their intersection. And thus this implies and implied, the last statement means the first set is subset of the last set, and conversely the last is the subset of the first set. And thus the relation becomes f inverse of x intersection y is subset of f inverse of x intersection f inverse of y and this set. Intersection of these two sets is subset of f inverse of x intersection y, and this gives the equality of the two sets. If they are subset of each other, then the two sets must be equal, and this proves the theorem. So this completes the proof. So thus we have proved two results, theorems about the inverse image of union and inverse image of intersection. Now we shall consider the third theorem as the image theorem related to the image. If f is a function from A to B, and now suppose x is subset of A. Here these are subsets of y we have written earlier. See, a subset of B we have written earlier, and now we will consider. So what is actually the meaning of this theorem? See, this is A set and this is the set B. So we have to consider, we have written x is subset of B and y is subset of B. That means x and y will be in the set B. This is set x, suppose, and this is set y. These are subsets of B, and the theorem says that inverse image of their intersection. If x is here, then its inverse image will be in A. So there will be, say, f inverse of x. So suppose this is the f inverse of x, and this is mapped to x, and similarly there will be f inverse of y, and this is mapped with y. F image of this is y and f image of this is x. Now what is the intersection? Their intersection will be this one, x intersection y, and the inverse image of this intersection will be the intersection of their inverse images. That means f inverse x and f inverse y, and their intersection is this one. So that means this region will be related to this region. So f image of this is equal to this, and inverse image of this is equal to this one. So that is the meaning of the result that we have proved. Now the third theorem we shall consider is f is function from A to B, x is subset of A and y is subset of A. Then f image of x union y is equal to f image of x union f image of y, or inverse the image of the union of the union of two sets is the union of the images. This is the union of the images. F of x union y is equal to f of x union f of y. Now here the situation is that x and y are subsets of A, not of B. So for inverse images we have considered x and y in B. Now we shall consider x and y in A. The meaning of the theorem will be, so suppose here is x set and this is y set, and their union will be the whole region which is in x, which is in y, and which is in both x and y. So and that is mapped to f of x, means f image of this will be somewhere here. So for understanding we are considering the figure. It is not necessary that this must be here, so it may be mapped to somewhere here also. And what will be f image of y? So that will be like this. So this will be f of x, and this x is mapped to, or the image of x is this set f of x. Image of y under f is f of y, that is this set. And what the meaning of the theorem is, f image of their union. So this is the union. This is the union of x and y, the region in both the sets. And this f union, the f image of this union is mapped to the union of f of x and f of y. So this is the meaning of the theorem. So that means this set this is f union of the these two sets. F of x union y will be union of fx and f of y. So these two regions are mapped to each other. So that is the meaning of the theorem, and we shall prove this in separate implications. So we shall first suppose say C is an element in this set, or we will consider B is an element in that set. Let first let B belongs to f of x union y. That means see f of x union y, so that is here somewhere, and therefore B is in this set that we have supposed. Therefore then there exists then or we can write then this B is equal to f of A. If B is in the image set, then it must have a pre-image, that is A. B is equal to f of A for some A. A belongs to x union y. So what we have considered is B is here. B is f of x x union y. So that somewhere here we have considered, and therefore this B will have pre-image A, and that will be in the union of x and y. So this implies, see, A is in x union y, means this implies A belongs to x or A belongs to y. It is in the union means it is in either set, x or y. And if A belongs to x, what this implies, B belongs to f of x. Or if A is in y, then that will imply B belongs to f of y. So therefore then B belongs to f of x or B belongs to f of y. See, if B is here, then it is B belongs to, if B may be here, then its image will be in, inverse image will be in y. So that is the case here. A belongs to x union y means A belongs to x or A belongs to y. This implies B belongs to f of x because A is in x, or B belongs to f of y. And further, what this will imply, that we want to show this belongs to fx union fy. So that means this implies B belongs to fx or B belongs to fy means B belongs to fx union f of y. And thus starting with B belongs to f of x union y, we have shown B belongs to f of x union f of y. That means this set is subset of this one. Every element in this set is an element in the last set, and thus f of x union y is subset of f of x union f of y, and we suppose this as first relation. Now we shall show conversely an element in this second set is also an element in the first set. Conversely, let, and we will consider the element as another element C. C belongs to fx f of x union f of y. This implies C belongs to f of x or C belongs to f of y. That means C is in the image set of x or C is in image set of y. Means C is an image. C is a image of some element in x or C is image of some element in y. Therefore, C is the image of some element in x, or C is the image. From this, C is the image of some element in x and C is the image of some element in y. C is the image of some element in y. So that means we are assuming here C is somewhere here. Then C is the image of some element here in x or here in y. If C is here, then its inverse image will be somewhere in y. And thus what this implies, C is the image of the some element in x or some element in y, means C is image of some element in x union y or corresponds to union operation. And therefore C is the image of some element in x union y. Some element in x or some element in y means some element in x union y, and this means, or this implies, C belongs to the image of some element, that is f of x union y. And see, we have started with C belongs to fx union f of y, and we have obtained C belongs to f of x union y, and therefore this set, every element in this set is in this set, and that implies thus f of x union f of y is subset of f of x union y, and we shall suppose this as second. Now you see 1 and 2. Here we have shown this set is a subset of the right side set, and here we have shown right side set is subset of the left side set, and if they are subset of each other, they must be equal, and hence we have the equality of these two sets. From 1 and 2 we get the result. we get this result, that is f of x union y is equal to f of x union f of y, and this proves the theorem. Now we shall write a remark here. What about this union is replaced by intersection, and that means whether we can we write f of x intersection y is equal to f of x intersection f of y. So if f is function from a to b, x and y are subset of a, then the result, this result, whether it will be true, and we will say that it is not true or need not be true, then the result need not be true. May be true, may not be true. So, or we can say it need this result is need not be true, may be false. That means this actually this result does not hold, because when we say it is true or it holds, if it is true for all cases, it must be true. And when to show it does not hold, one counter example is sufficient. The one example is sufficient in which the result fails. For example, we can say let fx is equal to say x square be the function, and let here x be the set. We will have -1 and say 0, 0 minus 1 we can say, or -1 0, and y be the set can be considered as 1 and 2. Now we will see what is f of x. Therefore, f image of x, we are observing this result whether it holds or not. F of x means the image of this, and that means -1 square. The function is f of x is x square. So image of -1 is -1 square, that is 1, and image of 0 is the same, 0, and f of y will be square of 1, that is again 1, and square of 2, that is 4. So this we have f of x and f of y. Now see we have what is x intersection y. Now x intersection y is, see the intersection of these two, no element is in common between x and y. These are discrete sets we have written, and not necessarily discrete, we can have the closed interval or open interval also. So x intersection y is phi, and if x intersection y is phi, therefore f image of x intersection y will be f of phi, and that is phi, empty set. But what is the f of x intersection f of y? You see f of x is 1 0, and this is 1 4, and 1 is common, and therefore it is 1, and thus here these two are not equal, and therefore f of x intersection y is not equal to f of x intersection f of y. Here it is empty, but here it is 1. So that means the result for intersection does not hold. The result for union holds, but not for intersection. Now we will define one more type of function, which is composition of two functions. How to define composite function, or how to consider composition of two functions. So we will write that as a definition. Composite function or composition of functions. Let f is a function from a to b. Let f from a to b be a function, and suppose g from b to c be functions. Then Then the composition of two functions. Composition of g and f, then the composition of two functions, composition of g and f is denoted by g naught f, and denoted by g naught f is a function or is function g naught f will be from a to c. Note here b must be common, that the domain, codomain of this f must be the domain of g, and is a function g naught f from a to c defined by g naught f of x is equal to g of f of x. So this is the composition of two functions, and you can say, consider the figure like this. Suppose these are the three sets A, B and C. Here it is A, B and C. F is a function from A to B and G is a function from B to C. And we have, if we have x here element, then that will be related to f of x. Image of this is f of x, and image of f of x under G will be g of f of x, and this is the composition function. That means from x to g naught, that is x to g of f of x. This is g naught f of x. So image of x under this composition will be g of f of x. That is the meaning. And for example, if you have let f of x is equal to 1 plus cos x, and here x will take the real number value from any real number, and g of x is equal to x square. Now this will be positive numbers. 0 is less than x is less than infinity, or less than or equal to. Now the codomain is non-negative real numbers, and this is also the range here will be also non-negative, because cos x maximum, the range of cos x is -1 and +1. If it is -1, then this will be 0, and if it is +1, then it is positive. So therefore this B set is common. The codomain of this will be the domain of this. And now what will be g naught f? Then g naught f of x is equal to g of f of x. And see what is f of x? F of x is 1 plus cos x. But what is g of x? G of x is x square, and g of 1 plus cos x will be the square of 1 plus cos x, and that will be square of this is 1 plus 2 cos x plus cos square x. And thus in this way we can form composition of two functions. And note that g naught f is not equal to f naught g in general. G naught f of x is not equal to f naught g of x. You can find what will be f naught g here. First g will be operated because this f naught g will be of x will be f of g of x, and in this case here it is f of x square. So g of x is x square, and what is f of x square? You can see f of x is 1 plus cos x, and this will be 1 plus cos of x square, and this is 1 plus cos square x, and this is cos of x square. So both are different. So this is the meaning of composition of two functions. So thus we have studied few results on functions in this lecture. Thank you.